Hello, this is Stephen Nesheba, and I'm here to help you out with the pre-lab and some of the first steps of this computational lab, ions and amino acids in aqueous solutions. So let me take you down to the pre-lab part of this and calculate the electrostatic potential mappings at the semi-empirical level of alanine and these other amino acids. So I'm going to go straight to Spartan, and here's how you'll want to do that. I've chosen the peptide menu item here as opposed to the organic or the other ones, and you'll see that all these amino acids are coming up, and I'm going to just choose alanine. Click over there, and there we have it. Now, the way that it appears here, it doesn't have actually a full complement of oxygens and hydrogens, and that's because it's set up to form longer chains, peptides. We don't want to do that. We just want to have this amino acid, and the way to accomplish that is to use this what's called the terminate button. And the terminate button says, how do you end up with this? And since we are sort of more or less an aqueous solution, I would like to have a deprotonated carboxylic acid and a protonated amine that would correspond to a pH neutral solution. So there it is. And now you'll just do the normal procedure of setting up calculations and so on. So I want to take us next to the next stage. This is actually what you'll be doing in class. Build a water cluster of 20 or so water molecules, minimizing the configuration energy in stages. So to do that, I'm just going to go collect a new one. Now, of course, we want to go back to the inorganic molecule, and I've already tab atom, and I've already chosen the oxygen and with 2 bonds like that. So there's a water molecule. And now as you double click on here, you'll be adding more water molecules, and you can rotate it around. And so there they are. I'm now going to hit this energy minimization. Now you'll want to put more water molecules on there, but here it's done that. And you might want to, certainly under model, pick up hydrogen bonds so we can see what sort of hydrogen bonds it's making. There are other things to look at here. The tube is sometimes a better way to examine some of these complexes. And lastly on this, to find out typical hydrogen bond distances, like from there to there, you go to this distance measure here, and this will pick up the oxygen on that water molecule, and that will pick up the hydrogen on another. And as you can see, it's come up with a distance of 1.8. You'll see a lot of variability, so you want to look at a lot of different hydrogen bonds to get a sense of the typical distances. Let's see, our next task here is to do a similar thing, but around fluoride and sodium and so forth. So I'll just do a new one, and I'm going to go back to this inorganic menu item, and there's fluorine, so I'm going to click that. Now we don't want any hydrogens on here, so I'm going to take them off. And now I'm going to go back to oxygen and double click around it and do our energy minimization. Don't forget to turn on the hydrogen bonds so you can see what's happening. And of course you'll want to add a whole bunch more water molecules onto that. So let's see, the next one, after you do sodium and methane, we're going to be looking at water clusters around some amino acids like alanine and so on. So I'm going to go back and show you how to kind of get that started. I'm going to choose another new guy here, and we'll go back to peptides. There's alanine, and I'll just click on there. Once again, we need to do this termination thing so we can protonate or deprotonate it appropriately. But now instead of going for a semi-classical semi-empirical calculation, we're going to do the same thing of putting some water molecules around it. So I'll go back to this inorganic menu. There's my water molecule, double clicking and so forth, and minimizing, and you can kind of see what starts to happen there, especially if you turn on the hydrogen bonds. So I think that's enough to get you started on this project. Thank you.